So my name is Adrian Sapio, and I'm with Link Labs. And I will be talking about end-to-end IoT solutions using long-range, low-power wireless networks. Bio slide. First, I'm an embedded systems engineer at Link Labs. I've spent the last 12 years doing embedded systems design and wireless communications, signal processing and control systems. My academic background, my bachelor's and master's are in electrical engineering, and I'm about halfway through a PhD in the same at the University of Maryland. So Link Labs is part of the Renesas ecosystem, proud partner. Okay, so IoT. So a good way to introduce Link Labs and our products, I think, is to make the point that IoT product development is very multidisciplinary. If you've worked in this, you know. If not, you need to know. There's a lot of different disciplines involved when we say Internet of Things. You have, starting from the bottom, you need electronics design, analog, digital, RF, microprocessor firmware development. You need systems engineers for the wireless links. Typically, this will go to some sort of collector or aggregator where you'll see Linux. So you need Linux experts. You need networking. You need, to an internet presence, you need software engineers experienced with building scalable cloud platforms. So these are a lot of different disciplines. And you want subject matter experts on all of them. And that's a lot of subjects. So what we find is that adding this connected intelligence to a product, from talking to our customers, they tell us it's a long and expensive process. And adding these wireless technologies, what they find is they go through this sometimes at large cost, and what they end up with really doesn't meet their performance goals, and the cost and the ROI is not what they expected. A third thing we hear is that they underestimated the complexity and the importance of robustness on this whole chain. So that's where we'd like to come in. So Link Labs, I'll introduce. We're a small company, about 20 employees. We're based out of Annapolis, Maryland. I'm over here somewhere, that's me. So we basically have been working in these technologies for the last, on average, 15 years for our developers. We're based out of DC, so we come mostly out of the defense industry. So we combine all these technologies to make an end-to-end solution, hopefully to turn over a product that a lot of customers won't need to bring in that expertise in-house. So the connectivity, I can explain it this way. So our customers, we think, are experts on the end over here and the end over here. So in this example, we have a paper towel dispenser. This is the thing in their Internet of Things. And this notional application of a smartphone that tells somebody in maintenance when it's time to replace the paper towels or change the battery. So you have an idea in mind for an application, and you have something. So what we offer is products for everything in the middle here. So on this end, we have our RF modules. They're small. I'll get into the details in a few slides. The implication is you take this small module and you design it into your product. Solder it down. There's a very simple interface over a UART. And you have a thing. It might send a message like, I'm out of paper towels. So all you have to do is communicate that information to the module through a very simple interface. And what we do is, with our access point, we set up a wide area network where these messages go through wirelessly. They get up to the internet, to what we call our Conductor, keeping with the symphony theme, and give you an opportunity to build an application to it. So we basically do the data communications all the way from the thing up to the application. So we'll get into all three of these. And when you buy one of these systems, what you're setting up is a low-power, wide area network. So the radios we use, they use Semtex LoRa technology. We use those radios on our modules. And with those radios, we create a low-power, wide area network. So it's not Wi-Fi, it's not Bluetooth, it's not LTE. It's a LoRa-based, low-power, wide area network. And it's completely custom. It's designed from scratch, all the layers. around Semtech's LoRa technology. So if you have a high data rate application, if you need to stream video, do things like that, there's LTE, 5G, there's the latest Wi-Fi standards. These are excellent standards. But if you don't need that kind of data, if you have, for example, the paper towel, you need to send a few bytes, you use a cellular modem, you're going to pay for this in cost and in the power that this wireless module is going to consume on your system. So this is really designed for a completely different application. It consumes much less power, 10 times less, 15 times less than something like this, and at much lower ranges. So that's the low power and the wide area part of it. Okay? So if you're designing a system and you need to add this wireless connectivity, you can put in a cellular modem. A lot of people do this. So these are everywhere. It's ubiquitous. But a lot of times it's too costly for an application, and they consume a lot of power. These cell modems can consume 3-4 watts. That's a lot. It's certainly not amenable to a battery-powered application if you want battery life of years. And then another alternative you might see is mesh networks, so Zigbee. Mesh networks can work well in certain applications. The problem with mesh networks is if you have a node and it wants to communicate something out, the mesh seems like a good idea because it can make a lot of short hops. But the problem that this has is the nodes that are around, they have to be listening for their neighbors. So that means they have to be running their receivers. They can't be in low power states all the time, or most of the time. So mesh networks, they're not really appropriate. If you have something where there's a lot of nodes, they're sort of regularly spaced, and the power budget maybe is a little bit forgiving, a mesh might be a good application for that. For everything else that we see, so we have this product, we call it Symphony Link. That's our branded name for this. So it's long-range, low power, covers whole buildings to whole neighborhoods, seamless integration. The data gets up to this data cloud, and you don't have to do much work on your end. You can focus on your application, whatever it is, the two ends of this connection. So we've had customers that have designed with our modules for 10-year battery life and 10,000 connections per gateway. Data communication is bidirectional. And for the range part, here's some data. Let me explain this, what we're looking at here. So we're based in Annapolis. This is where our engineering team is. It's a map of Annapolis and the surrounding area. We have one of our gateways on a tower. That's right here. And these little circles, we have a device, we call it a network tester. It's essentially a GPS chip with one of our modules. So it gets a fix on its position, and it transmits its position up through our module to the access point. And then here we've plotted where this thing was. So this is a drive-around test. And everything's great here. This guy's driving, goes this way, gets to about Queenstown before he breaks the connection. So this yellow line is a measurement. So this went 25 miles. It's about 40 kilometers, so it's really far. That's not to say that anywhere you put this, you're going to get 40 kilometers. So I really want to caution anyone who's working with these technologies from seeing these reported distances and then say, I'm going to install this and get this range. It's really more complicated than that, so I'll get into how to handle that. But this is the data. This is where we are. Yeah, blue implies the received signal strength. It's kind of backwards. Usually we see these in opposite color, but here where it gets really dark is the weakest. So minus 115 dBm. Yeah, so we're by the water. That's where we are. Yeah. Yeah. So the reason this range is so good is maybe threefold. We're by the water. That's really helping us here. This antenna is very high up. It's 700 feet up, which is not a typical height where most people can install antennas. And this terrain is relatively flat. So it's an important thing. And I'll talk more about how to handle the fact that customers want to buy these products and put them in totally different places. And how do you tell them what range to expect, realistically? It's an important thing.
In that test,
Yes.
driving test, is
Yes.
the unit inside the car or on top
I
of the
think
car?
these guys had an antenna
Outside
that
the
they
car.
put on the top, yeah.
So
Yeah.
this is not tiny antennas anymore.
It's about this big.
Yeah.
Yeah.
Okay.
Yeah, that's
So
right.
IoT.
Why not?
A lot of the IoT stuff has to be small for a lot of applications. So
Yeah.
it's just going to be integrated antenna versus a nice long width antenna.
Yeah. So we see applications where people have to mount these things in places they don't have the ability to put an antenna. But we see other ones where people are outside and they have a nice antenna.
Yeah.
So
Different
it all,
application.
okay. So customer use cases. So these three represent our three biggest customers maybe. We're not going to name them, but they're illustrative. So there's one application. It's an alarm system. So these guys had these residential alarm installations, and they were using cellular modems to connect them all. So what they did was they replaced the cellular modems with our modules. So one per house. You can have an antenna. And this is a dense residential application. So they have a few of our gateways, and they install them throughout a neighborhood, and they basically replace the cellular link with these modules. That's one. Another is a lock control system, so basically access control. So you have the module. Here you can have a big antenna, so the antenna is hidden somewhere in there. But you have an access point, and it's somewhere in the building, and you can connect all these things together and basically build the access control system. The third one is for a vehicle tracking system and a tarmac. So what these guys had, they have GPS radios and our module integrated together, and they sell a product that goes on all these little vehicles that fly all over the airport. So the application there is they want to track where all these things are, where they're moving, optimize their processes, all these things. So these are three cases where this technology works really well. And they're fairly different in terms of the wireless propagation. This is a dense residential area, so there's certain needs there, and that range there is a little bit different than what you would get here. This is a purely indoor propagation. All these nodes are indoors. The access point is near a maintenance closet, so it's purely indoors. And this one's outside, fairly wide open area, but it's outdoors. So three different environments, all with pretty good results. Okay, so now a little bit more into the details of the module. So this is our low power module, we call it. It has the Renesas RX111 micro and the Semtech 1276 radio. So the output power is 18 dBm, and the receive sensitivity coming from the Semtech radio is -140, which is a really good number. That's essentially how we get the long range. Where credit is due, it's because of the Semtech radio sensitivity. The sleep current for the whole module is 10 microamps. So this is how we get low power. Essentially, in your application, you tell the module, send this data, and it wakes up, it manages the communication of that data to the gateway, up to the internet, finishes that transaction, and then it goes back to sleep. So if you do that once a day, once an hour, the rest of the time, it's drawing 10 microamps. So that's how you get these really long battery lives, because it's that low. And that's coming from the Renesas micro. So we can get that power because of the Renesas micro. As far as the RF output options, there's three. For some people for some applications, we have a small PCB trace antenna here, really small antenna. So this is 29 millimeters, and the antenna fits in there, and it's not bad. There's an RF connector also, so you can take this out to a cable, mount it to a bigger antenna if you have the ability to do so, you should. And the third option is the RF goes through one of the pins, so you can wire it in. you might have some sort of very specific antenna for the installation. So that's the module. There's supposed to be some labels here, but they disappeared. So there's a UART interface, which is how you communicate with the module. So we run our firmware on here. You have something that gives it a command through a UART interface. And then we also bring out SPI, GPIOs, analog. So that's the module.
Can you write application on the module?
You can. We have some folks that are doing that. We're working towards making that as smooth as possible. Right now, it requires interaction with our engineers. But for a lot of people, that makes a lot of sense, because if you have basically a very simple sensor application, we bring out SPI. It'd be nice to just talk to the sensor and everything would be on there. You don't need a separate micro. You save the power. Yeah. The challenge there is that we're running the wireless protocol in the micro. So if you do anything else with the micro, there's the possibility that you interfere with the protocol. We have an RTOS. There is separation, but we're working to make that cleaner. But yeah, that's a common request, and it's a good idea in some cases. Okay, for the gateway, these two are the same electronics. They're just different enclosures. This is our indoor gateway. There's two versions of this one. One has a single receive channel, one has 8 receive channels. What that does is it gives us the ability to handle more capacity, more endpoints. It's basically parallel ingest of data. So the way you get an internet connection to these gateways, they need an internet connection, is if you have Ethernet, you just plug that in. So Ethernet backhaul is standard. If you don't have Ethernet where this gateway is, but you can get it on a Wi-Fi network, we have an option with a Wi-Fi modem inside. So you put in the credentials, and then it uses Wi-Fi to go from the end node, goes LoRa to the gateway, and then in that case it would be Wi-Fi to the internet. If you don't have Wi-Fi, a lot of people don't, we have cellular modems that go in there. So between Ethernet, Wi-Fi, cellular, you'll be able to get this on the internet somewhere. Yeah, they're configuration options. They're essentially PCI Express modules that we drop in. So there's a few slots in here, and we'll just put in whatever you need.
So with the outdoor module that
Yes.
you had 70 something feet up there?
It was not this one, no. No.
Something like that?
No, in that high one, we have the antenna all the way up, and then 700-foot cable down to it. It's kind of like how you see the cellular base stations. What's that? Yeah, he asked if this outdoor enclosure is the one that we had 700 feet up. Yeah, sorry about that. The answer is no. That 700-foot installation is just the antenna up there with a long cable down to basically a big little shed. These ones, people order and they put them on building rooftops. Okay, this product here, this is essentially the same thing. It has the same purpose as the previous one, the big gateways. It's just even bigger. It's a rack mount, 24 receive channels and 64 receive channels. Same connectivity options. Okay, all right, now we'll get into a little bit of the wireless protocol. So we deploy these products primarily in the ISM band here in the US, 902 to 928. The band is configurable. The radio actually has a really wide range, and we just have a configuration. We can move it wherever you need. So what this graph is showing is down here we have frequency versus power, accumulated power. Up here we have frequency versus time. So the ISM band, the 915 megahertz band, goes from here to here. That's it. So what we're trying to show here is there's a lot going on in this band, and there's sort of there's a problem that happens. We want these gateways. We want you to mount the antenna as high up as possible, so you can get the longest propagation possible. But the higher up you put it, the more that antenna can hear the transmissions from all kinds of other systems. So at our 700-foot antenna, this is what it sees. So there's essentially all kinds of other systems using the band. So we've designed for this case from the beginning. So we have interference mitigation basically designed into the protocol. It's meant for use in the unlicensed band. It's meant to coexist with all these things. Something else, sort of, I don't know, kind of relevant. Right next to this band where we are, it's really high narrowband energy. This is a paging channel. So, I mean, that's right next to where you are. So it's kind of a tough environment.
So that's unlicensed and it's frequency hopping?
Our protocol is frequency hopping, yes. That's right. The question was, is it frequency hopping? The answer is yes.
I thought that was built into the chip.
Okay. The question is frequency hopping built into the LoRa chip? The answer is yes, it is, but we're not using the built-in frequency hopping. The built-in frequency hopping is on a per packet basis. It's very short hop schedule. We don't use that. We use hopping differently. We wrapped hopping around that. So we don't use the hopping that's in the chip. I'll get into that in a second. Okay, I think just one or two brief slides on how the over-the-air protocol works. So the LoRa radios are half duplex. What that means is they're either transmitting or they're receiving. You got to be doing one or the other. So if something transmits while the other thing is transmitting, it's not going to receive it. So anytime something transmits, the other end needs to be receiving, and it has to be synchronized in frequency as well. So what we do, this is our protocol that we've designed, Symphony. So we break up time into fixed length time frames, and it's a time division duplex. So here it's referred to as downlink and uplink. So in each frame, there's a beacon at the start of every frame. That's this dark blue. There's information in the beacon that the end nodes use. And the gateway is in charge of the resources. So it decides what percentage of that frame will be for downlink and what percentage will be for uplink. And this is done, this is a dynamic scheduler. So every 2 seconds, this is calculated. So the reason why this is appropriate is because you might have an application that's purely uplink, a lot of sensor collection. You might have something that is purely downlink. You might have something that's 50-50. You might have something that has different modes. So this is dynamic, this scales. Here we have a frame that's purely uplink. Here's the opposite. So this is time versus 2 notional channels. This next slide, a little bit more in detail on the same concept. We have time on this axis and frequency on this axis. So this blue is the beacon coming from the gateway, and yellow is many nodes transmitting. So the gateway determines what portion of the frame is spent for downlink, what percentage is spent for uplink, again. But the end nodes are spread out in frequency. So the point here is this protocol really is designed for applications where you have many, thousands of nodes to a gateway. These ratios are what's expected. And the protocol doesn't schedule transmission on the end nodes. Like if any of you guys are familiar with LTE, anytime a cell phone wants to transmit, the base station schedules every transmission. It says you transmit here, you transmit here, you transmit here. That's how it's deconflicted. That's great at LTE data rates. We can't do that here because if you have thousands of nodes and you have low data rates, you can't do all that handshaking. It's too much overhead. So our protocol gives information in the beacon that allows the end nodes to spread out. They spread out in frequency, they spread out in time, they spread out in some of the radio parameters. So that's how we're able to ingest tens of thousands of nodes with our bigger receivers. Is it
a master-slave type relationship?
It is, yeah. Yeah, it's a star topology with the gateway in the middle, access point in the middle, and the end nodes around, and the gateway manages everything. Question was, is it a master-slave relationship? Yes.
What's the beacon interval?
The beacon interval is configurable. Typically, we're like 2 seconds. We've had a couple applications where we've set it lower than that, higher than that, just to meet some
That
different
implies that
requirements.
all the end nodes have to wake up at a regular interval.
They don't. They don't.
No, actually, the beacon can be the same.
They don't. No. The question is, does that imply that the end nodes have to wake up at the beacon interval? The answer is no. So the end nodes decide when they want to access the network. If you have an application, a sensor application, where something needs to report a sensor measurement every 10 minutes, you can go to sleep for 10 minutes. When it wants to transmit,
You wait for the beacon.
it wakes up, listens for the beacon. Yes, that's right.
So it has to be wait at least 2 seconds to see that. Well,
Yeah, yeah. So the way the question is, it has to be awake for 2 seconds to hear that. If a long time has passed, we assume no knowledge, and yes, you have to receive for 2 seconds. If it's going back to back, no, we keep a history of drift, so it doesn't have to listen for the full 2 seconds. It can wake up just before, factoring in the oscillator drift. Yep.
I always have to work at the start network, or can I work on point-to-point? And if I can, is there a way to implement the gateway function in a module and embed it in some?
Okay. The question is, do they have to operate in a star topology? Or is there a way to make it point-to-point? Can you put the gateway on somewhere where you have just the module of the gateway? This product is a star topology. We're working on some point-to-point protocols. Nothing's available yet. Yeah.
Does this imply that the beacon is not frequency hopping?
Question is, does this imply the beacon is not frequency hopping? The answer is yes. The beacon is not frequency hopping. However, the gateway monitors this channel for interference. If it thinks this is a bad channel, it moves to a different channel. So there's that aspect. So here it's shown on one channel the whole time, but if you watch it over time, it will actually move on different channels. Yeah.
How many nodes can a gateway support?
How many nodes can a gateway support? Depends. So it totally depends. So the case that we typically base these numbers off of is what we think is a typical application, if there's such a thing. An end node transmitting a 20-byte packet every 10 minutes. So for that application, for these gateways, we can support 10,000 nodes. Now, if you have an application where the node is doing that every 10 seconds, we can support a lot fewer nodes. So it completely depends on what the data throughput is, what the requirements are of the end nodes. But it's really designed from scratch with parallel receiver banks. The protocol is this way to ingest as much as possible.
I think you just answered my question. I was going to ask how many receivers do you have in the gateway, because that's going to determine how you do bands. I mean, if you have only one receiver,
Yeah.
it's get a little tough.
Yeah, the question is how many receivers. So in the biggest one, there's 64. So Semtech, so we have the 1276 radio on the end nodes, but Semtech also has, they call it their concentrator, which has 8, when you made it with 2 other chips, it has 8 receivers in parallel, all the demodulators in one. So we get that from Semtech. We just use their larger chips. They're basically made for this. So it's really nice ICs. 8 chips gets you to 64. Yeah, you'll notice there are multiples of 8. Right. Okay, all right. Next, how are we doing on time? We're good. Okay, next thing is I just want to talk about the link budget. Okay, so when I showed the slide about the range, I said how do you handle the fact that this range is different from someone else's range? Okay, if range is important, then you have to look at the link budgets. Anytime someone promises one of these networks gets 10 kilometers or 5 kilometers, what you should say is, okay, sure, let me see your link budget. So the link budget is the apples to apples comparison. Put our link budget next to someone else's link budget. And that's how you'll know which will give you the better range. If you guys have worked with wireless networks, I'm sure you know what they are. For people who haven't, let me just briefly talk about link budgets. The link budget, it's essentially a budget. It's like a financial budget where you have so much money and you give this much here, this much here, this much here, and you're out. With wireless communications, you have a link budget where more precisely it's the signal power. You have so much power. Power goes here, power goes there, power goes all these places. Where you want it is at the receiver of the other end of the node. So what you have is you start out with some power. So this is one case, this column. You start out with some power. In our low power modules, 18 dBm. There's losses, and some of it goes in the cable. There's losses. You end up with some number, which is how much is radiated. So we have 11 dBm radiated. That goes out in all directions, not just where you want it, it goes everywhere else. And then that's the first important part. The second important part is how much power do you need at the other end to receive the signal. So what you want, and that's called receive sensitivity. You want the lowest number possible. So you start out with some power, and then it decreases and decreases and decreases over this link distance until it's lower than the minimum that the other end can tolerate. So separate that distance out until as far as you can go. When you reach this point, that's the link distance. That's how far it can go. So with our numbers, you can tolerate 149 dB of path loss. So that's an excellent, excellent link margin. So that's comparable to basically where you have cell phones. I think with LTE, they're in the 140s. It's really good. If you work with link budgets, you know this is a huge number. So we can tolerate 149 dB of attenuation, of degradation of the signal strength from the transmitter to the receiver. So if you have some options you're evaluating, and you say, yeah, these guys say 10 kilometers, but these guys say 20 kilometers, look at the link budget. What's the path loss? Compare those two. You'll get the better range for the one with the better path loss. Okay. So another thing we see talking to customers that do this before is they get the LoRa radios and they say, well, the LoRa radio already does this wireless communication. A lot of it's built in. It has hopping built in. We don't need your protocol. We're just going to make this thing transmit, make this thing receive. We're going to do it. No big deal. And you can. There's nothing stopping you from doing that. What's that? Yeah, exactly. It's challenging. Semtech also has an alliance they call LoRaWAN, specifically targeting public networks. That's also a really good solution for a lot of applications. What we offer is the ability to stand up your own network end to end. And we have a lot of features built in. So you can do all these things yourself. There's really not a lot of magic. There's just a lot of staff hours already put into this. So these are the features you get for free when you buy this product. You tell the thing to send, and it just gets there. You don't worry about how, but it's going to get there. The reason it's going to get there, first of all, we have frequency hopping. So hopping is important because let's say you have an end node that tries to transmit here. The transmission never arrives due to interference. So the end node transmits, it's expecting an acknowledgement, never hears it because it never arrived. So it retransmits again in a following frame. But the next time it retransmits, it does so in a completely different band. So now you have time diversity, you have frequency diversity. So that's how we mitigate interference. Automatic acknowledgements and retransmissions combined with frequency hopping. This is how we mitigate the interference in the ISM band. Another thing we have, adaptive transmit power and data rate. So you tell the end node to transmit, it automatically selects the transmit power. There's also options on the radio settings. It picks them automatically. It picks just enough to get there reliably, but not more so that you're consuming power needlessly. Okay, there's another encryption. So we handle key exchanges, and we use them for AES 128-bit encryption on the data. Packetization. So if you have a slightly longer payload you want to transmit, if you can just put it, you can just transmit. You put it right in the radio. Tell the radio to transmit. A problem pops up, which is If you want to get the longest range, you have to set the radio parameters in a way that makes that transition possibly longer than 400 milliseconds. And FCC says you can't do that. You have to send part of it here, part of it over there. So what we do is we take your message and we break it up and we send it in packets. We send it in different parts of the frequency. So that's how we were able to get this certified. And you don't have to worry about it. That's the point, is you just send your message regardless of length. Don't worry about the certification. It's in compliance. We have quality of service tiers. So this is if you have an application where some of the nodes might be more important than other nodes. Like if you have lots of sensors collecting data and you aggregate them to control something else, turn something else on and off, that thing you're turning on and off individually is more important than one out of maybe the 1,000 sensors. So if you run into a situation where the network gets congested for some reason, maybe all 1,000 nodes try and do something at the same time, you really shouldn't design it that way, but if it does happen, the gateway can prioritize resources to the more important node because you've configured it with a higher quality of service. Network reconfiguration. So there's some network optimization parameters that you would want to tweak. So what we do is we allow you to set those at the gateway. You can do that remotely through the internet connection, through the internet. And the protocol propagates that down to the end nodes. So some of the changes will affect how the end nodes behave. That gets propagated down. It's built into the control channels. So you don't have to go and touch something on those 1,000 installations. It's completely done from the internet. You can address nodes individually or multiple nodes, roaming support. So you can have multiple gateways as part of your application. That application on the tarmac, they do this. So there's a gateway for this area, gateway for this area, gateway for this area. That little car drives from one area to another. It will change the connection from the one gateway to the other. You don't even find out about it. It's like a cell phone in that sense when you're driving. So that's built in. You can do all this. This is $1 million development effort you're going to have to spend, or you can get it for free, nearly free. So this is version 1. This is version 1. We sell these. These are very popular right now. What we're working on is version 2. I think the latest estimates for these features are Q2 of next year. This isn't available yet for sale, but we do have these working in the lab. So the big feature this adds, which people ask for, is repeaters. So this is a one-hop repeater. This is a completely separate device that you install. It's kind of a dumb repeater. All it does is take the traffic from the end node, receives it, retransmits it, all within the protocol. Both directions, up and down. So it gives you an additional hop. Now, it's just one. You can't take two of them and have 2 hops. They don't support that. They don't have the routing necessary for that. So that's the repeaters. Some other features, the interference avoidance gets a little bit more sophisticated. There's a gateway API. This is for applications where you might not have an internet connection, maybe agricultural applications. So what we allow you to do is write applications right on the Linux box. So you can have the whole thing off the internet, off the grid altogether. That's a feature we're working on, and something everybody wants, which is over-the-air firmware upgrades. Very important. We don't offer it yet. We are working on a file transfer protocol to do this. So Q2 next year. Okay. I think there's just 2 slides here about some of the communications options. So the uplink direction, end node to the internet, there's only one option. You send it and it gets there. There's some minor options like whether you want these acknowledgments and retransmissions or not, but for the most part, there's only one case here in this table. For receive, so the opposite direction of information flow from the internet down to the end node, we have 3 options. So there's a really important trade-off here, which is how often are you going to run the receiver on your end nodes? If you have it always on, we call this always on, that's the lowest latency case. You can address the end node whenever you want. It'll receive the message as long as it's in range. And that latency from the internet down to these nodes is around 2 to 3 seconds. The problem with that is you have to run the receiver all the time. So I think these are about 20 milliamps 20 milliamps is what they consume with the receiver on. So that's not going to get you years of battery life with a reasonable battery. So we have lower power receive modes, mailbox receive mode, and periodic receive mode. What these do, we talk about mailbox, is essentially you address a node or many nodes. Our system routes it to the proper gateway, and the packet stays at the gateway. When the end node, basically the way you set up your end node, you can set this up to check in every 10 minutes, 20 minutes, 1 minute. It wakes up, it asks the gateway, do you have any packets for me? Yes, no, yes. Packet comes down. So that's a way to get a command from the internet all the way down to the end node. But in the case of a 10-minute period, the end node spent most of those 10 minutes completely asleep, drawing that 10 microamps. So you run the receiver just when you need to. It could be on your schedule based on your application. And one more slide. And these two columns here show some calculations for these options. Always on periodic mailbox. This is for 2,000 milliamp hour batteries, so like 3 AA's. So the always on mode, latency of 2 seconds, but you will run these down in 13 days. So what we typically advise is only use this in AC powered applications. And some people do that. If you're AC powered or you can tolerate this type of current draw, and that's how you'll get that latency, sure. But if you're looking for years of battery life, by making that period 10 minutes, this becomes almost 5 years. So that's how we get a low power downlink mechanism. And again, this is for a 20 byte message every 10 minutes. So this is kind of a baseline we use to compute these numbers. If we change these numbers, those numbers change. So you need to adapt it to what your application is going to use. But this is kind of a baseline that we compute things on. One more thing. Yeah, the adaptive power. So what we have here is 2 cases. One where 146 dB of path loss are needed, and one where 20 dB less were needed, 127 dB were needed. So for a node that tries to transmit, again, the 20 byte message every 10 minutes, if it's close enough to the gateway, or if it has a good, it's in a favorable position where it doesn't need the full link distance, the end node, the module will turn down the power, select the radio parameters differently to still close this link, but do so consuming less power. So if there's a node that can be in this situation, for the same exact communication, we can turn a battery life of 2.8 years to 6 years. So almost doubling the battery life automatically, just with this adaptive power and data rate. So this is all in the firmware of the module. Okay, I think it's just one slide. Yeah, this is very detailed. Don't worry about all the details here. So I've talked a lot about the end nodes, the gateways. The third big part is the internet, the cloud-based software that we have. So this is a big overview. So we've talked about modules and gateways. So what the gateways do is they communicate via secure connections to this big software thing we have on Amazon Web Services. We call it Conductor. So what's here is where all the data is. Network management, configuration control, APIs. So when you send a message from the module, you get it all the way at the other end. So we have an API, basically a web address. You can hit it all day long where you can fetch your data. So Conductor. You can access this via like a machine-to-machine interface, which is how something would ultimately be deployed. You can build a front end. We have a little front end for you to just kind of play around with this while you're doing prototypes. So you go to the web address Conductor. It's kind of a dashboard for when you buy these gateways. You register them under your account. you can see your gateways, your networks. You can say these gateways are in this network, these gateways are in this network. Basically, this is all under your control, how you want to label things. You can provision your endnotes to different applications. So back to that tarmac application, you might have one thing that's moving the suitcases around, one that's got the thing with the stairs. You can say these are different. You call them different applications. You can manage your users. So then you click on an application, you say, show me all the little cars that drive suitcases around, and it'll show you in real time the data that's coming. So this is just a way to kind of visualize. It's not really made for a final solution. I mean, it can be a final solution, but this is just an example of how to hit the web addresses with some sort of software to pull this data out. This is really the machine-to-machine interface. This is what this previous slide, this is a front end for our API, dataaccess.linklabs.com. Secure, you got to have the right credentials to access any of this. So what you do in the form of, you build a query, say, give me all the data from this gateway for the last second, something like that. And this is a HTTP post, HTTP get. What you get back is JSON, standard JSON content, something like this. What this is these are all the packets I've received in the last second, a big list. So we have obviously the message, this little thing that the paper towel dispenser said, I'm out of paper towels. Obviously that's there, that's probably the most important part. But we also tack on timestamps, signal strength, channel number, there's some more metadata. So we give you lots of data. You can ignore most of it if you want to, but we tack on a bunch of things. And you can pull this. And this is scalable. This is on Amazon. This is all made for scalable web services. So this was architected anticipating really high throughput, tens of thousands of nodes for an application. Okay, I think we're coming to an end here. So our development kits, these are for sale, linklabs.com. There's a couple options. There's also a third one that's not shown here. So what we have is a USB-based development kit. It's essentially our module in there, surrounded by a USB connector, some pins, a reset button, RF connector. Okay, so what you would do here is you get a gateway. You get this USB kit, plug it in USB. On here, we have software that you run. It could be Windows, Linux, or OS X. Supports all three. And we have a command line interface here. So this is amenable to scripting. So what you can do here is kind of try out an application without having to get into any electronics design, right? It's plugging in USB cable, that's it. And you can wrap the command line utility around a scripting language, and you can send your payloads or simulated payloads. You can pull that down off the back end. So you can basically stand up an application with this development kit. We also have a range test GUI. So the way this works is the development kits, I think they come with two. So you configure one of them for this mode. And then if you were to power it off a battery, got this one battery powered. This one's USB powered. You run our GUI, which is this little user interface, got some graphs, real-time data. You put both of these things in this mode just by clicking through. And what you can do is you can take one of these and walk around with it. And it's basically just transmitting LoRa packets, receiving LoRa packets. It's basically testing bidirectional communication, and it's showing you the signal strength, how much margin you have. So this gives you a way to kind of walk around with one of these in your environment, whether it's urban, indoor, outdoor. And this isn't running Symphony. This is just really testing out the LoRa chip. Semtech also has some development kits that do this kind of thing. Either one will probably give you the same results. We have a third one, which is beta testing right now. It's not shown here. We call it our network tester. Small, handheld battery-powered thing. It's got a screen on it and a GPS. So that works with the gateway. So the way that works is you get a gateway. You either buy one or maybe a vendor can bring one by. And you plug it in wherever you think you're going to be able to mount a gateway. And then you can walk around with this network tester device. And on there, There's a display that's showing you the signal strength, margin. It has GPS, so you can drive around with it if you want. So that's really the way to see, okay, I think I know what the range is going to be, but I have hills, or I'm in an urban environment, or there's this thing blocking me. So this is how you really see what the range is going to be. That's very cheap. You can do that before you commit to a design. They range in price. The cheapest ones, I think, around $500. Yeah. Question was, how much is a gateway? I don't know where the question came from. The modules, they're, depending on volume, I think we can get them down to around $20 for the modules. Don't quote me on this. I'm not the best one to talk to about prices. Take my card afterwards. We'll get you a real quote. Yep.
Can a gateway handle more than one repeater?
Yes.
You can not restart to the radius?
Yes. Can a gateway handle more than one repeater? Yes. Yes. The ones we're designing now, I think we're allowing them to handle up to 8 repeaters, but that limitation is becoming a little bit arbitrary. We're not really limited by it. It's just one of the configurations. Yep.
If you use one of your gateways, do you also have to use the Conductor software, or can you use your own backend?
The question is, do you have to use Conductor? Yes, you have to use Conductor. What we do for people is we give them the ability to just pull out raw data, not use a lot of what we offer. That's really all we have at this point. I think what you need, if that becomes a problem, if you can't use Conductor, if you just don't want to use Conductor, what you have to wait for is the Gateway API that we're working on. Q2 next year is the estimate. What you can do there is write a little bit of code on the gateway where you can create your own internet connection. You can have that go to your server. You can have it go to wherever you want. One last thing, on our website, there's a tool for link budgets. So what this allows you to do, I know you guys can't see it, that's really small. It's got little sliders here, and it allows you to set the values for your planned installation. So transmit power, that just comes from us. We'll tell you what that is. Gateway antenna height. This has an enormous effect on the range. Where can you get an antenna? If you can get one 700 feet up, you can get one on just a building. If you can get one basically wherever you can, set this slider appropriately. A couple other things. What kind of data rates do you want? That affects the receive sensitivity. So you adjust these sliders and you get this range. This has been fairly accurate for us, the model behind this. And this web page also says view assumptions. If you click that, you can see all the math behind here. So we're not making, there's no black magic. We're just plugging these numbers into some fairly common models. You can argue the models if you want, but that's at least the calculation. And this tells you, for your application, what type of range to expect. It's not 40 kilometers. It's not 10 kilometers. It depends. It really depends. So this should be the first thing you do. And then as you get more serious, get a dev kit, borrow a dev kit, and walk around with one of these and say, OK, yeah, this range, this is going to work. And you go from there. And that's all I had. So please complete the survey form.
Did you try that building? Inside a building?
Yeah, we get really good performance in buildings just due to the huge path loss that we can tolerate. Yes, but okay. So the most recent case, we had the antenna on the 36th floor of a skyscraper, and we could go down to the 2nd floor, so 34 floors. But the reason I hesitate to throw that number around is because this is a big glass building, and the propagation we think is mostly through outside. So I can't say that that's a typical number, but it's gone through 34 floors, at least in one case. It might be typical, I don't know. It might be that no matter what you do, it's always going to go through the outsides. So we find it.
You had an antenna outside or inside?
No, totally inside. Gateway was inside. The end nodes were inside. Yeah, and yeah. Yes.
Do you have low battery notification
We don't, because we don't provide batteries on the module. What we do is we give you the ability to measure a battery and send that up. And that's a very common thing. Everybody does that who has a battery-powered node. You want to measure the battery, and that voltage is one of the things that you want to send up every few hours. Yeah, we don't explicitly do that for you.
Yeah, but I mean, it's not part of the protocol, right? You come up with your own message and send it up.
That's right. Yep.
Now, you indicated you're working on over-the-air firmware upgrade.
Oh, yes, that's right.
Wouldn't that blow your battery out to Kingdom Come?
Yeah. Yes. An over-the-air firmware upgrade will require a receiver to be on for an extended period of time. So for some of the payloads we're looking at, 10 minutes, 15 minutes. So you have to plan for that. If you think you're just going to do a firmware upgrade every week, well, you're going to drain your batteries. So
They
that,
get once in a lifetime firmware upgrade.
yeah, yes. So that has to be part of your engineering design decisions. Is what's a firmware upgrade going to be? Is it going to be something that should rarely ever happen but can get you out of a jam, or is it going to be the way that we push upgrades every week? Well, if you have a really restricted power budget, you can't do that second case. Yeah.